Welcome back. We're going to spend a second day talking about graphing these radical functions. Only today we're going to focus on cube roots instead of just square roots. So cube roots take a slightly different shape, have a slightly different parent function. If you note over here, they kind of look like this twisted S. Okay? Now, it should look familiar for you because you know what a cube function looks like. Okay? So since you know what a cubic function looks like, notice this is just kind of tilted on its side. We're going to have a conversation about that come a couple sections from now about what that connection is, why they look so similar, just slanted. But that's a basic shape you need to know because that's a basic shape you're going to be maneuvering around in this section. So the steps are actually exactly the same 3 steps as previously, as last night's section with radicals or with square roots. Except this time our table is going to be slightly different because we only want to use nice values, okay? I use an x of -8 because I know the cube root of -8. I know the cube root is -2. I use an x of -1, again, because I know its cube root is -1. I use 0 because I know that its cube root is 0. And then I use 1 because I know its cube root is 1, 8 because its cube root is 8. So basically my goal is using nice cube roots to construct this table. Just like yesterday I used nice square roots to construct that table. So my first order of business is going to be graphing those points. All right, so there are my points that are going to give me kind of that crooked, slanted increase. Now I need to move them around. Now I need to talk about my transformations. Well, this is sending it to the right 2. That is sending it up 3. So I'm going to graph based on transformations. Now that I know that that's what I'm doing, I'm going to take every one of those points and shift them around. So I'm going to start with that left-hand point. Right 2, up 3 is going to land it right there. Right 2, up 3. Then the one at the origin, right 2, up 3. The one that's at 1, 1, let's move it right 2, up 3. And then that last one over at 2, 8, or 8, 2 is going to be right 2, up 3. So once I shift the whole thing around, now I just connect the dots, and that's what I get. Now, the really, really cool thing about these cube roots is the domain and range. The domain and range are really, really easy because notice it's extending in every direction forever. So what that means is I have no restrictions. I can put in any x value, get out any y value. So that means the domain and range are super simple. Both of them for these cube roots are always all real numbers, which again is super, super nice that that's the situation that we're getting. So that's all you need to remember about these. Cube roots gives you all real numbers. So let's move on to our next example. Now this example starts utilizing the table, okay? Because notice I have that stretch that's incorporated in my equation. So remember, I include that stretch in my table. I'm going to multiply every one of these values by 2. Once I've done that, well, now I'm done with that middle column. Okay, and remember that table always starts the same way. You always use the numbers that you know how to take a nice cube root of. And now I'm just multiplying them by 2 like that says 2. So that's my first transformation, a vertical stretch of 2. And now I have my points I'm going to plot. -8, -4 puts me right there. -1, -2, 0, 0, 1, 2, and 8, 4. Okay, so I plot each of those points that's in my table after applying the stretch. And now I'm going to shift them around. Recall this right there is going to send it left 1. That right there is going to send it down 4. So every single point I apply that to. So starting at the point down in the left corner, left 1, down 4. We'll land it right there. Left 1, down 4. The one at the origin, left 1, down 4. The one sitting above the origin, left 1, down 4. And the one in the right-hand corner, left 1, down 4. So recall, I take each individual point, and now I connect them up to get my shape. And recall, the neat thing about this shape is cube roots have no restrictions. I can use any x value and can ultimately get out any y value. So both of these have a domain and range, all real numbers. Any x and any y are possible here. All right, let's move on to our next one. So, for our next one, once again, we have something that's going to be utilizing our table. We have that negative out front. Remember that x-axis reflection uses a table too. So I'm going to incorporate that in. So each of these values, I'm going to multiply by a negative 1. So essentially just flip the signs of each of those y values from my parent function. And that's going to be what I graph. You always incorporate a stretch or x-axis reflection in the table. And now those are the points that I'm going to put on my graph. So negative 8, positive 2, negative 1, positive 1, 0, 0, 1, negative 1, 8, negative 2. So notice all it did is it really just flipped my graph over, okay? Which is totally fine. That's what was meant to happen. Now let's see what else is happening. So here it's being shifted left 1 and then up 5. So those are now the translations that I'm going to do. That's how I'm going to slide it around. Left 1, then up 5. So that's where that left-hand point will go. Now those 3 in the center, left 1, up 5, left 1, up 5, left 1, up 5. Then that 1 over to the right, left 1, up 5. So after I slide it around, now I connect them up. And now I'm ready to interpret the domain and range. But the neat thing is, in that interpretation, there's really not much you have to do. Because again, realize every x and every y value can be used. So both of these end up being all real numbers. So really nice turnout, really nice scenario for this. That's all you have to remember. Well, beyond graphing, let's talk about what if we have something that looks more complicated? Okay, what if we have something that look like those equations right there? Well, the goal is you can actually do some slick factoring and you can get it to the point that it could actually be graphed. I'm not going to make you graph it, but it's kind of cool just to show you how you can manipulate these. Looking at the first one, what I want you to notice is if you pull a 9 out of both of those, you get something that looks like that, don't you? Well, the interesting thing is, though, that you know the square root of 9. So because you know the square root of 9, I'm just going to call that out and pull it out and call it a 3. All the x plus 2 is going to stay inside. So by factoring out that 9, I can actually get it completely out of the square root. And now I have something, those are actually basic transformations Well, that thing could actually be graphed now, because now I just have a vertical stretch of 3, and it's being shifted to the left 2. So again, not that I'm going to make you graph it, but I'm just showing you what you could do for these more seemingly complicated not variables, complicated equations. You could simplify them by using that basic factoring. Well, what about this one? Well, this one I can pull an 8 forward. Well, easy enough, I actually know the cube root of 8. I know the cube root of 8 is 2. So I'm going to pull that out of there. And now notice what I have left is something that can be written out as a basic set of transformations. I have a vertical stretch of 2, left 4, and down 2. So that's going to be another skill that we're going to work on more in class and with your practice work, but it's something I want you to be aware of. Seemingly complex things can actually be a little bit simplified. All right. Now, I do want to show you, though, how your graphing calculator can sometimes help you with some of these more difficult problems. So let's take a look at this. You can model the population P of Corpus Christi, Texas, between the years 1970 and 2005 by the rational function that, where x is the year. Using this model, in what year was the population of Corpus Christi 250,000? So we want to know, when was that population 250,000? All right, well, oh, I'm sorry, I wrote that wrong. Forgot the 75,000 there. Now, back in section 5, we actually discussed how you could end up solving this, right? You isolate the cube root, so take 250,000 divided by 75,000, and you end up getting 10/3. Now you want to cube that. So take that and cube it. Well, when you do, 10 cubed is 1,000, 3 cubed is 27. And now that you have that, now let's add 1,950 to it, and you get about 1987. Okay, in 1987, the population would hit 250,000. Now, I just want to introduce you to the idea that graphing these things can actually also help you. So there's a slick way to do this on the calculator. So let's take a moment and talk over that. So if you have your calculator handy, why don't you pull it on out for me? So the first thing you want to do is input the function. Okay, so in Y1, you're going to input that function, 75,000. Then go into math. That's where your cube root is right underneath your cube. Then x minus 1950. Now, let's do some troubleshooting here. So if I just were to hit enter right now, I'm not going to probably see almost anything. In this instance, we're going to have to play with our window. It says the years is between 1970 and 2005. So that's going to be the window of the x values that I'm looking at, okay? And then if we're looking for the population when it hits 250,000, well, That's going to be our y. Our y's are the populations. So let's just go up to 300,000 in the population. Okay, so I'm just adjusting my window so I can actually see what I want to. Well, that's my graph. Okay, now it doesn't quite look like we'd expect just because we're seeing a very small snapshot of it. This thing is really, really, really stretched out. Now we're curious, when is it going to hit 250,000? Well, let's see. Population is y. So if I put in y equals 250,000, what that's going to do, oh, I'm sorry. I have to fix this. There you go. I'm sorry about that. So if I put in what line represents a population of 250,000, that's what that red line represents. Okay? That is the point at which a population is 250,000. So we want to know what year does our blue graph cross that threshold of 250,000 people. So back in chapter 5, we worked a lot in this calc menu. All right? So finally, we're going to get to number 5. I want to show you option number 5 and how it's going to help you with this. Because this is going to find the intersection of where those two touch, where those two cross. All right? So I want to go to the left, and then I want to go to the right of where I think they intersect. There's my guess, and notice there it is. That 1987 that we found algebraically is also graphically where they cross. Now, is this going to be important? Is this going to be something I test on? Well, I'm not going to assess you on this, but it's something cool that I want you to know, that your graphing calculator can do a lot more than you think. Okay, you don't have to do everything by hand. The calculator is very handy at solving certain things for you. All right, but I think that is going to be all for our notes today. So I do want you to write a summary for me. There's a lot of good things we talked about. So this time I'm not going to give you a prompt because I think hopefully you can figure out some of those key points to highlight. So do make sure you write that summary for me and then come back ready to do your practice work.